let's take a look. So for just a quick revision, bases. Okay, bases are either one of these two. So when these two react together, acid plus base, we get two products. We always get a salt and we always get water. That's all. So characteristics of alkalis and acid. Let's try to list as many as we can over here. So next time I can reference. So in terms of physical properties, I'll put a P there for physical. So we have things like sour taste. And then we have bitter taste for alkaline. And also this one, we also have feel soapy. So all the taste and physical touch for these two. Then another physical properties that is together with the both, for both acids and alkalis, we say that they are generally good electrical conductors. In an aqueous solution. Okay, this is for both of them. Okay, the rest of the category, we won't really put them under physical properties, but just, I think characteristic is fine. pH less than 7, pH more than 7. Turns blue, litmus red. Turns red, litmus blue. Okay, these are the generic ones. Okay, you know question, let's go to number 2A. Okay, we can say either ionizes or dissociates. H plus ions in water. And also depending on your schools, you may need to say as the only positive ion. But otherwise, anything before that should be okay. Part B, sodium carbonate reaction. We react with nitric acid. Okay, this one you all have already done the last lesson, the word equation. By right, you all owe me homework, but I think none of you remember. Then I will settle the homework by next week. I'll remind you all again about the homework. Okay, so let's settle this. This is the chemical equation. Can we try to write this up? Give you all a minute to do this. The ions that you need, sodium ions. Carbonate ion look like this. Nitrate ion, H plus ion. Okay, so these are the ions that you need. And give you all a minute to sort this out. Let me go through. right? So this, because it's an acid carbonate reaction, we will get a gas, which is CO2. You'll get water, and the salt that we get will be sodium nitrate. Because of the nitric acid will produce nitrate salts. So sodium nitrate, we have NaNO3. And to balance the equation, we need to put a 2 in front of Na for the sodium. And then because of the 2 nitrate, I'm going to put 2 in front of the acid. Okay, that's all. Okay, testing for carbon dioxide. Okay, we'll just say test the gas. With lime water, also known as calcium hydroxide. So if there's a CO2 present, white precipitate form. This white precipitate is calcium carbonate. Okay, those in bracket, we don't need to write. I just want to show you what is it.
Wait, must we know what the precipitate is?
Good to know.
Need to know? Oh, good to know.
Yeah, is very good to know. It will appear in practical exams.
Oh, okay.
Okay, question 3, we will skip. There's no space to do this. The homework part, right, that y'all owe me, y'all will do all this practice. Right? So for this worksheet, we won't do question 3. We will skip. Same thing for ionic equation, we will skip. Everything, all this will be cleared in the worksheet before. So we can ignore this for today. All right, next, let's look at strong acids. We say that they undergo complete ionization or complete dissociation of H+ ions in water. So our other strong acid in syllabus, we say that other than hydrochloric, we have only nitric acid and H2SO4. All other acids, we say that they are weak. Okay, next, a base substance that react with, we say that with acid. Okay, to form salt and water. Soluble base, we call them alkaline. So alkalis normally is in a form of a soluble metal hydroxide. Okay, so over here, I think more accurately is example of soluble base or examples of alkalis. These are the only ones in syllabus. Group 1 hydroxide, calcium hydroxide, ammonium hydroxide, or also known as aqueous ammonia. Okay, this is the very standard list of alkalis. All need to memorize. Okay, let's go to number 6. In generally neutral solution. We can understand this by saying there's a few ways to understand this. So I'll give you a few options. Number 1, generally there will be no reaction with alkalis or acids. Number 2, you will also want to understand this as they have equal concentration of H plus and OH minus ions. Okay, so what do we mean by this? Remember, the H plus ions accounts for the acidic properties. OH ions accounted for the alkaline properties. So normally for acids, the H plus is more than the OH minus. And for the alkalis, the OH is more, the OH ions is way more than the H plus. So that makes the respective solution either acidic or alkaline. So when you have equal concentration of H plus and OH minus, so you are neither acidic or nor you are alkaline. So that makes this solution a neutral solution. Okay, for part B, it's the same thing, salt plus water again. Okay, so for part C, you can see that when these two react together, the salt that is formed, sodium sulfate. So under separation technique, if you evaporate a solution of sodium sulfate, the substance left behind will be the salt itself. So this one also don't know what they're trying to ask, but it's actually there is this 1 mole and 1 mole thing, right? Actually has an impact. The real answer is actually not sodium sulfate, but for now we don't touch on this. Ryan, this one I did review before. It's the replaceable hydrogen thing. But yeah, for now, for every one of us, we just take it to be this first. Let's ignore the impact of the 1 mole and 1 mole thing. Okay, for question 7, can I give you 1 or 2 minutes to sort out the alphabets for this? Then we will check the alphabets together. Question 7, let you all try this out. So far, anyone with questions? Then let's check through the answers for this. First two is AF, I think should be all right. CD should be all right also. Right, any questions from A to D? Okay. EF for E and F, right? Will the pH change? I think for O levels, we take it as no. It should technically remain the same. Most of the time we put as the same, it should be all right. But in actual fact, there is going to be some changes. But that portion will be a little way out of it already. But I can do a simple explanation to you why the pH may change. But technically, right, you see what your teacher says when you're doing acids. What happened to dilution of the alkaline solution and dilution of an acidic solution? Does it cause any pH changes? But fundamentally, right, it shouldn't change. Fundamentally, it shouldn't change. Oh yeah, Zikri, what's up? Okay. So let me do a simple explanation why the pH may change. Okay. Just for concept sake. So for O levels, let's just put it as remain unchanged. We see what your teacher says. But let's say we talk about another possibility why it may change. Let's talk about adding water. Because when you add water, you're doing dilution. Ada, what do you think is the direct impact of adding water to any solution? Doesn't need to be acid alkaline. What happened to
the concentration decreases?
Correct. No matter what you do, no matter what solution, what kind of substances, as long as you add water to the solution, the concentration will decrease. This is more or less will happen. So if the pH actually does change, right? Okay, due to the addition of water, if the pH does change, okay, this can be the simple explanation. Okay, so what is the simple explanation that we can give for dilution causing changes in pH? Remember, we always say dilution shouldn't do anything much at O levels. But in the event that your teacher say that is a change, and explain why the change occurs. Okay, so like what Ada mentioned just now, that is a change in the concentration. So let's talk about the alkaline. So when you add water, the impact is the concentration of the OH ions that is in the solution will decrease. So now it is deemed to be less alkaline. And because it's less alkaline, then the pH will actually decreases. So it actually moves closer to pH 7. Move towards pH 7 because now it's more diluted. In a similar case for acids, okay, if you add water, similarly the concentration of the H plus ions in the solution will also decrease. So when this happens, it becomes so-called less acidic, and the pH, we say, will increase as it moves closer, also to pH 7. Something like that. So actually there's this question, if I have an acidic solution, right? If I add water to it, we say the pH rise. Is it possible to keep adding water, right? Until the point that it becomes neutral. Is it actually possible? I would think it is mathematically possible. Okay, the solutions you generally still have OH ions, or for the acidic solution, it fundamentally still have H plus ions. Adding water doesn't remove the H plus ions. The only way you can remove the H plus ion is by reacting it away, by adding a base or a carbonate to react with the H plus. That is the proper way of removing the H plus, not by dilution. That's why there is this paradox thing that some teachers, I don't know which part they are trying to test you. So you have to be very reactive in the exam. So in all cases, right, when you do dilution, it shouldn't remove the H plus. So it shouldn't change the pH. But if it does, it will be the explanation over here. And if you do actually, right, in mathematical sense, if you add so much water, into it, right, the concentration of the H plus ions become diluted by so much, right? It becomes like neutral solution, really. A simple explanation I can give you is this. When you take a drop of lemon, you drip that drop of lemon into your mouth directly, right? You feel that it's super sour. Why? Because this more concentrated acidic solution basically has a lot of H plus ion in a small drop of lemon. So you feel that it is very, very sour because it is very, very acidic. So if you take this same drop of lemon, you squeeze it into a giant pot. No, I don't even need a giant pot. You put it into a bowl of water. You drip that same lemon in. When you try to drink it, you probably won't taste the lemon at all, really, because it's so diluted. So if you were to do a blue litmus test, I'm pretty sure that drop of lemon, if you drip it on the red litmus, or you drip it on the blue litmus, it's going to turn red for sure. But will that bowl of water with that one small drop of lemon turns the blue litmus red? Probably may not happen because it's so diluted. The concentration of H plus is so insignificant, it doesn't produce enough to change the color. Okay, so for this particular question for E and F, you have to be reactive to what your teacher says in the question. Okay, right. If no question, can we look at number 8? Okay, give you a minute to look at this. Orange juice, right? So most likely it's acidic. So it should be your 1 to 6. So now the sour taste has been removed by the sugar, but that doesn't mean the solution is no longer acidic. Remember, the only way to remove the acidity is to remove the H plus. Adding sugar doesn't remove the H plus. Adding sugar simply cover the sour taste. So the H plus ions are still in larger quantities. So for this case, the pH will still be 1 to 6. Okay, so there is a colorless gas and odorless gas produced. This is a metal. So remember, metal plus acid, we get a salt and we get hydrogen gas. So the gas we produce here, hydrogen. And how do you tell the presence of the gas? Again, we'll write down the test. Okay, this is the standard test for hydrogen. Yeah, please help me jot this down. Those who are done. Oxides. The two major classification is whether the oxide is a metallic or a non-metallic oxide. So that's the two major classifications. So the two classification is either metal oxide or your non-metal oxides. And under metal oxides, we have two different metal oxides. The first metal oxide is called basic oxide. Okay, they are aka your bases. So as a metal oxide, they are considered a base. So in this case, generally, this basic oxide, I'll put as BO, basic oxide, they will react with acid to form your usual salt plus water. So metal oxides is a base, they react with acid to form salt water, very, very natural to do it. Okay, this is a very natural reaction. And also, if they are metal oxides that are soluble, they will actually form alkaline. They will form alkaline. Okay, so this is how we will classify basic oxides, which is part of the metal oxides. Okay, anyone with questions regarding basic oxides? Okay, if no question for this, the second type of of metal oxide amphoteric oxides. I'll put as AO. Okay, because they are metal oxides, right? Ashton, what do you expect it to react with? Since it's a metal oxide, you expect it to react with?
Is it metal?
Because it's a metal oxide, right? You look at basic oxide. Basic oxides are metal oxide also, right? So if you look at this topic, right, metal oxides, they have the ability to react with something. Like for example, magnesium oxide, okay? It can react with something, right? What do you think it can react with? Something very familiar.
Is it hydrogen?
Like the acid, right? Can I say that it can react acid? The
Yeah.
hydrogen part, right? So metal oxides, they have the ability to react acid. That's very normal. So do you think amphoteric oxide, as a metal oxide, right, it will also react acid to form salt and water?
Yeah.
Should be, okay. So let's talk about this. Amphoteric oxides, because they are also metal oxides. Okay, they will react with also acid to form salt plus water. This is very normal. This is a very normal thing that will happen. However, the thing that is not normal, and hence there's this special categorization, is because amphoteric oxide, they will also react with alkali to form salt and water. Okay, this reaction is not normal. It's not expected of metal oxides. So that's why there is a few metal oxides that fall into this category. And I normally remember them as Z, which is ZNO, zinc oxide, Al2O3, aluminum, and PbO, lead. Okay, these three of them are your only amphoteric oxide in syllabus. And the only reason why they are not classified with the rest is because of their ability to react with alkaline, which is not a normal reaction expected of a metal oxide. Okay, so this is the portion for metal oxides. Right, any questions for the two kinds of metal oxides? Any question, please sound up. Did not give you a minute to digest this. Then we go to the two different kinds of non-metal oxides. So for non-metal oxides, we have two categories. The first category is acidic oxides. Okay, so this one, okay, this oxide, they will actually, because they are acidic, Zikri, what do you think is expected to react with? Because it's acidic, it should react with? What say you? As an acid, it should react with? You say something like, because I cannot hear you.
Salt, is it?
They form salt. But what do they react with to form salt? There's only two categories only. So if they're acidic, they should react with. The thing can be found in your basic oxide. What does it react with in the basic oxide?
Water.
No, you will react with alkalis, right? Because acid react alkali, alkali react acid. Right? So because these are all acidic, so they are likely to react with alkalis. So when they react alkalis, right, basically what does it form?
Salt.
And?
Water.
Yeah, correct. And if these acidic oxides are soluble, they will actually form acids. So the non-metal oxides, if you can dissolve them into water, they will turn into our acid. Okay, so that's all for the acidic ones. So this one is just a little bit like your basic oxide, the usual, but the very usual, no exception case. For the other part is totally different. This is your neutral oxides. And for neutral oxides, okay, because they are neutral, there's no reaction with acid or alkaline. Totally no reaction at all. They have a pH of 7. And the ones that we need to remember is number 1, H2O. H2O is a neutral oxide. Number 2, the monoxides. And in particular, nitrogen monoxide, which has a formula of NO. And carbon monoxide, which has a formula of CO. Okay, so this is what you're expected to know for the classification of the 4 different oxides. So with this in mind, can I give you a couple of minutes to do question number 9? Question number 9 is just classification, very straightforward. based on what we have above, classify the different oxides into their correct category. Basic, amphoteric, acidic, or neutral. Okay? Yeah, give you a minute to try it out. So first off, you need to know whether, okay, normally the amphoteric very easy to pick up, zinc, aluminum, lead. So we already got the aluminum over there. So this one should be amphoteric oxides. And then the monoxides are easy to pick up also. There are two monoxides over there. So these two should be your neutral. Okay, then no more. The rest is either a metal oxide or a non-metal oxides, because we already picked out the exception cases. So so this is a metal, non-metal, non-metal, metal, and non-metal. So very quickly for the metal oxides, right, we'll classify them under basic. And for the non-metals, this will be your acidic oxides. So as we know, if so the whether they are soluble or not, and whether they can react acid or not. Okay, all these are based on the reactions above. So if they can react with acids, for example, the basic oxides, they form salt and water. The acidic ones, they react with alkali to form salt and water. Okay, all those stuff. Okay, any question? Okay, if no question, can we look at question 10? This one got a bit of description, but it's also classification of oxides. Yeah, take a look and then we do together. So for 10A, it says blah 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 react water. Then the outright thing here says turns red litmus blue. That means this is an acidic solution really. And as we said before, it says all this with water, right? Over here we say that, oops. Okay, if it's soluble, it will form acids. This part here. Okay, if the acidic oxides are soluble, it will form acids. So we can safely consider A to be an acidic oxide. Part B says it forms a colorless solution when it is warm with acid and alkali. That means this item here can react with both alkali and acids. And there's only one category which will do this, which is our amphoteric oxides. We say that it is normal for the amphoteric oxide to react with acid, but it is not normal for any metal oxides to react alkali. That's why we have this special category of metal oxides that react with both. So for part B, because it has the ability to react with both acid and alkali, this falls under the category of amphoteric oxide. No reaction. There's only one of them. They say that these neutral oxides, they don't react with acid or alkalis. So this one's straightforward. For C, you'll be neutral. And the last one, it says the solution will turn it blue. So this is an alkali form. So when it's an alkali form, it's definitely this guy here. If soluble, it forms an alkali. That means the oxide must have previously been a basic oxide. Okay, any question for this? Okay, if no question, let's go to the next portion. 11, we cannot do it because of some solubility. 12, we cannot do it. Okay, this is a strong acid. This is also a strong alkali. So for the strong ones, 1 and 14, take the extreme corners. So universal indicator, neutral is green. So I don't know I draw this before, let me draw this again. Remember this as colors of the rainbow. These are the acidic ones. The neutral is green. The alkali ones are blue and purple. Universal indicator. Strong alkaline. Weak alkaline. And then for green is neutral. For both of these is weak acid. For the red is strong acid. Okay, so that's our options here. Okay, part 2. In terms of the ions, the difference in the alkalinity of these three solutions. So as we mentioned just now, when your solution is acidic, you have more of one of them. So for the acidic solution, so for HCl, I'll say, don't use the word number, we use the word concentration. So we have a concentration of H plus more than the concentration of OH ions, because the question says, explain briefly in terms of the ions in the solution. So for water, because it's neutral, the concentration of the H plus will be the same as the concentration of OH minus. And for the alkaline, we'll have the concentration of the OH more than the concentration of H plus. Okay, that's all. Okay, give you all a minute to jot this down. Then look at part B. Part B is based on this reaction. This was one of the equations that you all wrote the other time. Okay, so for this, it's not just alkaline, right? It's any base. Base, also known as any kind of metal oxide or metal hydroxide. So in the question here, you have your ammonium salts. The calcium oxide is the base. So it is exactly this reaction we're talking about. Okay, so what happens when you do this at the same time? Okay, he wants to do two things. First, he wants to neutralize the soil, and then he wants to fertilize the soil. So let's talk about the role of the calcium oxide and the ammonium salt. The calcium oxide here as a base, his purpose of adding this into the soil is to neutralize the soil. And the purpose of the ammonium salt is to fertilize the soil. Ammonium salt has the ability to fertilize the soil because by fertilizing the soil, we are talking about introducing more nitrogen into the soil. Okay, why nitrogen is essential? Okay, because for the plants to grow, they need to have plant proteins. Plant proteins essentially, one of the important elements is nitrogen. Okay, nitrogen is the base of plants and animal proteins. So in order for plants or animals to grow, there need to be an injection of nitrogen. So in this case, right, the plant protein is, or rather the plant growth is enhanced by ammonium salts because of the nitrogen present. And if the soil is too acidic, it is neutralized by the base, acid-base neutralization. Okay, so first off, you need to understand why the farmer actually add those two items. The calcium oxide to neutralize the soil, the ammonium salt to fertilize the soil. But if you were to do these two things together at the same time, it is bad. Because if you look at the equation over there, ammonium salt and a base, they generally will react together. So the moment they react together, then the farmer's objective to fertilize the soil is gone because the nitrogen is supposed to go into the soil. But what happens now is that the nitrogen turns into ammonia gas from the equation over there. So that's the case, right? The fertilizer that he adds in doesn't inject more nitrogen into the soil. Instead, the reaction, because of these two, is added together. The nitrogen will be escaping to the environment as ammonia gas. So in a way, he wasted his fertilizer. And then the base supposed to react acid went on to react the fertilizer. Then the soil remains kind of acidic. So both the base fail his job to neutralize the soil. The ammonium salt also fail his job to neutralize the soil. So if the farmer wants to do this, okay, he wants to neutralize the soil, he wants to fertilize the soil, he should do it separately. These two reactants shouldn't be placed together at the same time. Okay, so let's explain why putting this at the same time, he's wasting his time and money. Okay, this is my answer, and this is the standard answer. A bit squeezy, let me put it here, okay, 14B. Okay, it's due to this particular reaction that the whole purpose is to introduce nitrogen into the soil, and because ammonia is now produced, it's lost into the environment as a gas. So this gas that's lost to the environment doesn't increase the nitrogen content in the soil. So if the nitrogen content of the soil is not increased, then it's a wasted fertilizer. Okay, something like that. Okay, give you a minute to look at question 15. I'll leave this here for you all to copy. Right, let's look at question 15. Acidic always produce, so acidic is always H+. Soluble basic oxide, this one also known as alkali, will be OH. Okay, pH strongly acidic is 1. Just for content's sake, weak acid in a range of 3 to 6. Weak alkalis in the region of 8 to 10. And then for the strong alkalis, we will put it as 14. Okay, acid alkaline, again, this process is called neutralization. And we did so many times, they will always form salt plus water. Every time you have an acid with an alkaline or with a base, it's always salt and water. Okay. Yeah, those who are done, you can proceed with part D. We'll let everyone copy this first. Okay, after this question 16, last question, we'll call it a day for tonight. Today is a lot of oxide stuff, good time to introduce. So we'll finish with question 16, then you all can call it a day. Don't want to drag too long for you. After dismissal, Zikri and Ashton, you all stay back. Short while. So part D says some oxide react like acid, react like a base. That means when it behaves like an acid, it is actually reacting with alkali. When it pretend to be like a base, he's reacting with acid. So since he react with both this kind of oxides, we call it amphoteric oxides. Okay, remember there's only 3 of them: ZAP, zinc, aluminium, and PbO lead. And this lead is known as lead-2 oxide. The aluminum and zinc should be straightforward. Okay, let's finish up with 16 and then we call it a night. So Ziyi, I will prepare your stuff and then I'll text you separately. Then after I dismiss Zikri and Ashton, stay back. Okay, let's finish with question 16 first. Okay, let's settle the few very direct ones. Okay, you're supposed to know that quicklime is another name for calcium oxide. Okay, the outright no explanation required. I'll do it first. Basic oxides, you should have your metal oxides. So we have sodium and we have calcium. Amphoteric, there's only one. ZAP, we only got the A over there, the aluminium oxide. Okay, let's look at DE. Acid rain is caused by, if you're the job people, you all should see all the industry stuff, right? Where they burn fossil fuel and all. And then the acidic gases escape to the environment. And then the acidic gases dissolve in the rain clouds and it falls as acid rain. So which gas are we talking about? This is in one of the later chapters. The gas responsible for acid rain is actually sulfur dioxide. And another one that is not present over here in the list, nitrogen dioxide. Okay, it's not in the list over there, but it's also responsible for acid rain. So good to know. Okay, and then for part E, found in car exhaust, there's quite a lot of gases found in the car exhaust. The two most common ones carbon monoxide and carbon dioxide. But for this question, the answer is this, because of the word poison. Okay, CO2 is also produced, but it's not poisonous. Okay, so I just put it as to let you know. So now let's do a quick one on why carbon monoxide is actually poisoning. Okay, although it is neutral, but it has the ability, right? It actually forms a stable compound with hemoglobin in the red blood cell. So as a result of this, right, this will actually inhibit or actually prevents the red blood cell from transporting oxygen. So in less severe cases, this can lead to suffocation. In severe cases, it can lead to death due to the suffocation itself. So this carbon monoxide can lead to the poisoning of blood. So the blood gets poisoned because of the stable compound with hemoglobin. F don't need, it's okay. But the answer here is carbon dioxide. One of them burns, so the two of them, right, is actually carbon monoxide. When you burn in oxygen, you get CO2. So the two of them, the one that says when one of the other burns, this is the one. Produce is this one. I produce CO2 when CO is burned. Something like that. I'm not that important. The rest, very, very good to know. Okay. Any questions from everyone? Today, main thing is we did a lot of oxides. It's quite important. And just now when I go through, right, randomly asking a few questions, some of you a bit not familiar with this. This should be some of your next topic. In fact, most of you should be doing this for the next topic. So before school reopen, do review, look through the notes one more time. So when school reopen, we got one less trouble. This is a very horrendous topic. Okay, so yeah, let's go and look through. If there are no questions for me, right, that's all for me. Those who need to wait for my private message.